Hi everyone. Recently, I have watched a movie named Deadpool and Wolverine, and I loved the movie a lot. So, while watching that movie, one thing popped in my mind is that can we actually become Deadpool? So, one interesting fact about the movie is that both of the superheroes has similar superpower, which is healing superpower. But I want to aside Wolverine because Wolverine superpower is pretty much he got it by born, so he's actually a mutant. But on the other hand, Deadpool is different. Deadpool got his superpower by some kind of cancer, and he's actually a mutate, not a mutant. So, as from the movie, we got to know that from Deadpool 1, he got his superpower by a treatment from cancer, and cancer may be a terrible disease, but it may just give Deadpool its superpower. Cancer is so peculiar that if you cut one tumor cell in half, the one tumor cell will be different from another tumor cell. So Deadpool actually got his superpower with two genes. One is oncogenes and another one is tumor suppressor genes. So they are actually work as a gas and pedal. So oncogenes actually help tumor to grow, and the proto-oncogenes to help the tumor to die. But as I am not an expert in this field, I'm going to talk about it with Professor Amadeo Parissenti. His research expertise is in the area of molecular pharmacology with a particular emphasis on chemotherapy drug resistance in breast and ovarian cancer. Dr. Parissenti serves on the Tissue Banking and Breast Correlative Science Committee of the Canadian Cancer Trials Group. He and his research collaborators recently developed an RNA-based test to monitor the effectiveness of neoadjuvant chemotherapy in cancer patients. The test is being further investigated and commercialized by Rna Diagnostics Incorporation, a company for which he currently serves as Chief Scientific Officer. Dr. Parissenti Research Group and the RNA Diagnostic Research and Development Laboratory are located at the Health Science North Research Institute, where Dr. Parissenti had hold a scientific position. He has a postdoctoral studies on Harvard Medical School, and he has done his postdoctoral studies in University of Toronto. Currently, he is a full professor of Department of Chemistry and Biochemistry in Laurentian University.
Wait!
But first, let's get into the intro.
Should be good now.
Okay, Professor, thank you very much for letting me to give me the opportunity to talk about you. Like this very much for me, some people it's maybe silly, but I think it's interesting, and I just want to start the conversation with that. Have you ever heard a superhero named Deadpool before?
Have I ever heard of?
Deadpool, the movie that's actually coming on. It's a Marvel superhero.
No, I'm not. I'm not. I don't know any characters.
Okay. Okay, so that's actually would be interesting. So Deadpool actually a Marvel superhero. So there is actually two
Okay.
giant comics book that actually in USA. So some people actually likes the DC and some people actually like the Marvel. So DC
Yes,
is actually
I've heard of
the
that.
Superman and the Batman, and Marvel is actually the Iron Man. I think you have heard the name.
Yeah, I've heard of those. Yes.
Yeah, so
Yeah.
the thing is that so they actually have made a movie based on their superhero, which is named the Deadpool, and it has another superhero. Its name is Wolverine, and these two is actually very interesting because they have a similar kind of power. You know that every superhero has actually a kind of superpower, like
Yeah.
Superman,
Yeah.
Batman.
Yeah. Yeah.
So the Wolverine, he actually has a capacity of healing superpower. So
Healing
yeah,
superpower.
he if
Okay.
you cut him, if you do anything, he will actually have the healing capacity, and he will actually be as normal as he was before. But the thing is
Can
that
he heal others as well, or just heal himself?
just he himself. He cannot heal others,
Heal others. Okay.
and he can actually like bring a like sword of kind of things from his like from this from his
Yeah.
face. So
Okay.
he can actually cut through these things, and he's so super strong. And
Yeah.
the another thing, another superhero is the Deadpool. He also has a kind of healing capacity. So the thing is that the Wolverine, he is actually called the mutant because he actually gained his superpower through his birth. So it's not, it's a natural thing.
Okay. He gained his superpower from his
From his
body.
birth. So from his birth, he actually gained that. Like it's naturally coming from his birth. From the day one, he has
Okay.
the power. But the Deadpool
Okay.
is actually a kind of different superhero. So the story is that he got actually lung cancer, and he actually contacted
Lung cancer.
lung cancer, and he actually contacted some underground researcher. They actually do some like fishy things under the cover, and they actually do something on him, and
Yeah.
he signed a paper. And then what actually happened, they actually do research on him. They want to do something, but things gone bad. And what actually happened, that all of his body cell actually turned into cancer cell.
Okay.
So the thing is that if you cut him, if you there is actually a movie scene where a villain actually teared him apart from his from his navel part, and then he actually come again with regenerating body. So interesting, because the thing that we are actually we all scientists are actually trying to heal cancer, trying to
Yeah.
suppress the cell so that
Suppressed cancer. Yeah.
it actually don't blast or don't actually grow so much that eventually it actually come to an end for a human being. But
Yeah.
in the movie, they have done the reverse.
Yeah.
They have made all the cell of the that Deadpool is the cancer cell, so he cannot die.
Yeah.
Yeah,
He's immortal.
that's a
He's
superhero.
immortal.
He cannot die. So my question is, you are in this field so many years. So
Yeah.
like, have you ever like have any kind of idea that is that possible to make the any human organ to regrow?
Sure. So yeah, there is evidence that you can do that in the laboratory to get tissues to grow.
Okay.
It not to the point that you are able to create a tissue with a blood supply that you could then introduce back into a human being. Like, say, for instance, you had a defective heart, that you could
Yeah.
grow a whole new heart outside of the body and then put it in the body. No, not at this point. No.
And I think as far as I have studied, it's because in our heart or in our kidney, the cells are actually different. So if there is any cut actually happen on our skin, so the skin is actually they are all like the same kind of cell. So it's actually very easy to regrow or regenerate this kind of cell on our upper surface. But if anything happens
Yes.
to our heart, so there is actually complex structure of every part of our heart. So that's actually that's why it's so hard.
Yeah, because the heart is permanent. The heart muscle is permanently differentiated. So if it's damaged, it can't grow more myocytes. It can't do that.
Yeah.
Instead, what happens is the cells get larger. They undergo hypertrophy to try to compensate for the damaged muscles. Yeah.
Yeah. So but if we actually look around our nature,
there's some creature that actually can regrow their organ. Like if you have seen lizard, they can actually regrow their tail. If
Yeah,
you
like the liver can do that, for example. The
yeah,
liver can grow.
because the liver cell is actually much more similar. That's why they actually yeah.
Yeah, we call those cells, there are various levels of stemness.
Yeah.
And so liver cells, the liver has stem cells. They're
Yeah.
not pluripotent stem cells that there are, for example, in our bloodstream that can create any type of blood cell. So
Yeah.
they're limited in terms of their ability to form, but they are less differentiated. And as like that's the one thing that is common between tumor cells and natural stem cells that are in our body is
Yeah.
that they have more they're more flexible in their gene expression. They're less differentiated.
Okay.
But other tissues in the body are permanently differentiated, and they don't grow at all, like nerve tissue, for example. Yes, there we go.
Yeah. So this is actually this is a picture of salamander fish.
Okay,
So
yeah.
the interesting fact of this creature is that it can grow any kind of cell of his human body. It can regrow its eyes. It can regrow its like it's a fish, but it has like little hands. It can regrow its hands. Anything. If you just cut it in even half, it will regrow itself. So the thing is that the researchers actually found out that it has a very potent oncogene cells. So when you cut it in half, the oncogenes
Yeah.
actually got so active. So it's like a you are driving and you actually press the gas pedal, and the oncogenes actually start to grow the cell. And then when the organs actually get it formed, then the tumor suppressor cell actually get it to its work. Then the breakdowns happen, and they actually
Yeah.
have their organ every time. It's like a
Yeah, and that's one of the things I even stress in my course on molecular basis of cancer, that oncogenes are really normal genes in the body that are expressed inappropriately, either at higher levels or at the wrong time in development. So these oncogenes that you're referring to play a role in development, and they can. That's the beauty of them.
yeah
The difference between tumor tissue is uncontrolled
yeah
cell proliferation, and it doesn't form highly organized tissues.
yeah
Tumor tissues are usually poorly differentiated, and they don't form discrete organs or structures or that type of thing. Unlike
yeah
your example there, where these are oncogenes, but they're actually normally expressed as they should be in that creature.
So like my question is that, can we actually use like oncogenes in the cancer cell to like make it in a form, or make it something that can be actually a good for human being? Like we are trying to suppress the tumor cell.
Yeah.
So like is there any idea to like reverse it, to give it?
Yeah. So what essentially you're trying to do is to permit it to go backwards, to differentiate, so that, see, the problem with tumor cells is that they have a lot of plasticity in their genome. So they can, and by plasticity, I mean they can express pretty much whatever protein they want to express. Where normally, as we undergo cell differentiation, we only express a mere fraction of all of the genes that are within our human genome. So what you're asking is, can you go backwards? Can
Yeah.
you cause cells to essentially differentiate from undifferentiated tissue?
Yeah.
And it's possible. And some of the things that have been described along that route is that there are certain hormones that essentially control the differentiation. So, for example, even in the laboratory, you can you can differentiate monocytes into macrophages by just adding one specific chemical. And what that does is it changes the gene expression and actually reduces the flexibility of the genome. It makes it more differentiated, more organized, less flexible. So is it possible to do that? Yes, theoretically. I don't know of any case where you have a tumor and you can get it to redifferentiate back to the normal tissue again. Partly because once tumors are cancerous, they're highly invasive, so that they move all over the place. And when they move to a different location, they can then change expression and adapt to the new environment. And so you're trying to control something that actually is under less control once it undergoes dedifferentiation and becomes more flexible in terms of its gene expression. The other thing is, because tumor cells are so invasive, they end up in other tissues with them. So really, in order for a tumor to then be useful, it has to be able to go backwards and redifferentiate back into and suppress its genome, a lot of it. And so in some cancers, for example, you don't just have, in some human cancers, you don't even have 2 chromosomes. You might have 6 or 8 copies of a chromosome. Well, that's very, very hard then to suppress the expression of 6 or 8 chromosomes to get it back to the level of it was before a cancer became dedifferentiated. So the big problem with that whole approach is that cancerous cells are genetically unstable. And you're trying to put the brakes on again and to suppress gene expression such that you can get tissues to differentiate again. I think you might be able to achieve reverse and get a little bit more differentiated tissue. But I don't think you could ever go back to the highly differentiated state that would represent an organ. Now, that's very different from your salamander creature, because those aren't tumor tissues. They still, even though they have what are called oncogenes, they're normal genes. They're under exquisite control. They're only expressed when they need to be expressed, and then they're shut off. These are not tumors. That salamander is not a tumor.
Yeah. So it's pretty much hard to become a Deadpool if anyone wants to in real life.
Yeah, I would say so. But then again, one of these things about science fiction, you don't, for example, I always liked, Star Trek has been around forever.
Yeah.
But the idea that you could travel to distant galaxies and distant stars, we all know. We all know that in order to do that, you have to become almost massless, because in order to achieve that rate of speed,
then it will not be any matter anymore.
That's right. But then in Star Trek, you reassemble that matter again. That is a really hard thing to do, to create a whole bunch of molecules and then somehow get it back into living tissue. But science fiction is all about what if, right?
Yeah. So let me ask you a serious question. And I think you have already talked about that we are actually fighting against cancer like so many centuries. We have we actually even fought and won against COVID. I think we have already won. We have fought against like tuberculosis, that was actually very much deathly. We have fought against plague, leprosy, and many kind of deadly disease. But it's getting so much hard to own against cancer. And we have some ground like on first stage or second stage cancer, but it's really getting hard to cure a person in their third stage. So
Oh yeah, third stage, you mean stage 3 cancer?
stage 3 cancer.
Yeah, even stage 2 is difficult. You know, stage 1 you can get a curation in some cases, but that's because the amount of tumor and it hasn't invaded. The whole idea then is to, at stage 1 you have local control, and as long as the cells haven't disseminated throughout the body, you can, you know, use radiation or surgery and then followed by radiation. You can pretty much kill that tissue. And so you've essentially tamed cancer, but that's by destroying it completely. Yeah.
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 So yeah.
That being said, but one of the things I will say is you can tame cancer by such that, you know, with specific drugs or agents, you can cause them to be less differentiated, to be more differentiated, to suppress their growth, so that they don't grow as quickly. They don't replicate. Yeah, so they're not less invasive. They don't replicate as quickly. And the goal, this is the case for a lot of cancers these days, is you essentially turn it into a chronic disease. You never ever cure it, but you just constantly keep it at bay, so that in the end, the person ends up dying of some other disease rather than their cancer. But you don't completely eradicate it. But stage 1 cancers, you can completely eradicate them with surgery and radiation. Not always, but it depends on the cancer. Yeah.
Okay, Professor, thank you so much. I just have one last question, and
sure.
And we can actually end this conversation. It was very good conversation, I would definitely say. So in the world, according to World Bank, so the average lifespan of human is now 71 years old. That's a huge. But do you think that in this century we can actually cross the 100-year lifespan of human? Is that possible?
Absolutely. Yeah, absolutely. Yeah. And in fact, well, one of my cousins, I was in France to celebrate her 100th birthday with her. She lived to be 104. And a lot of people, like at one time, this is, of course, before you came to Canada, but when I was a young adult, they used to wish happy birthday to anyone who, in the national US networks, they would wish happy birthday to anyone who was 100 years and older. And that was a pretty rare event. So, you know, you might have that happen once every 2-3 months. Now you'd be constantly wishing happy birthday, happy 100th birthday every day. So a lot of people are living now to 100 is not completely rare anymore. It's quite commonplace. One of the things, a lot of the experiments they're doing right now in animal systems is that if you can reduce the metabolism, slow down metabolism. Fasting animals, for example, will live much longer than animals that are allowed to eat as much as they want for as long as they want. And so there are things that we know that can affect how rapidly we age. And part of the aging problem, at least this is one of the models of aging, is that we have metabolism, but it's not perfect. So every time we metabolize compounds, there are residual pieces that remain. So even though say our body creates a protein, and eventually that protein becomes non-functional anymore. Eventually what will happen, the body will degrade it. If it's within a cell, the cell will place that damaged protein into a lysosome, and that lysosome will essentially then degrade that protein into individual amino acids, and then those individual amino acids can be used to make new proteins, right? So it's like the recycle machinery, and the lysosomes will recycle nucleic acids, lipids, proteins, everything, right? But the problem is that with each round of cell division and with increasing metabolism and everything that you bring in, the body isn't perfect into breaking it down. And so what happens eventually is the lysosomes, as we age, get bigger and bigger and bigger. And so you look at old people, they have these very large lysosomes.
Okay.
And you might have heard of this disease. It's called progeria. Have you ever heard of progeria?
No.
Progeria is a genetic disease where essentially there's defects in certain lysosomal enzymes.
Mm-hmm.
And so what happens then is, because these lysosomal enzymes aren't working properly, you build up garbage. You don't recycle all of the proteins or lipids, whatever. And so they build up within the lysosomes, and the lysosomes get bigger and bigger, and they start to interfere with the ability of the cell to function. So there are some theories that if with fasting, with regular fasting,
Mm-hmm.
and certainly not being overweight and these type of things, you can extend the lifespan, because your lysosomes will only enlarge very, very gradually over time. That's a model. And one of my students is actually in California at this Aging Institute doing interesting studies in this whole area of metabolism and how it's connected to aging. So I think the issue is, as we learn more, and I think what happens with people that age longer, they have more efficient metabolisms and less errors in their genome, and as a result, their cells can last longer than the average person. Yeah, so I see a lot of people now. The average life expectancy in Canada for a female is 85, 86. And for a male, I think it's almost approaching 80 now for a male in Canada.
That's good, because we are just 20 years.
That's right. So
we are getting that.
That's right. And it's even more important for me because I'm much older.
I am definitely sure you will live more than 100 years, Professor.
Thank you. I hope so too.
Yeah, thank you, Professor, for giving me the time. Okay.
Yeah, you're welcome. Take care.